Hey everybody, we are live now. I think the latency is working. Maybe it's really long. Oh no, it does seem like we're on long latency. It's like 8 seconds. Maybe I was in the past. But we'll figure it out. If you're here, we can take all the questions. It is cold today. It's cold in Texas. What's going on with it being cold in Texas? Let's over here start doing some review for 201. I don't even know how to talk. Let's start doing some 201 review. Okay. So the topics in 201 for this exam are decision trees, randomness. We have here chapter 10, which is going to be sample surveys. And then we have chapter 12, which is going to be probability. Chapter 13, part 1, that is going to be sampling distribution of sample proportion. And then chapter 13, part 2, if you're here and want to ask a question on these, there's going to be confidence intervals for the true proportion. A little difference right there. So if you have a question on any of these, we can do any one of these. We can cover any one of these topics. So when it comes to the confidence intervals for the true proportion, what we're talking about right here is the following equation. Let's look at that equation. So confidence intervals for the true proportion. Where's the right pen? We're going to go right here, and we're talking about the equation p hat plus or minus z, and then square root p hat q hat over n. That is the equation for that chapter. Very important right there. P hat is the true proportion. Actually, P hat is the sample proportion. Z is the confidence interval test statistic, which gives us the level of confidence. P hat right here is the sample proportion again, and Q hat is the complement. So whatever, if Q hat is 0.8, P hat is 0.2, vice versa. They are complements of each other. They add up to 1. N is the sample size. So however many are said are sampled in the problem, like if we sample 100 or 200, that would be the sample size. Sampling distribution of the sample proportion has some important formulas too. We should know here that the distribution will be normally distributed with a mean of P and a standard deviation of P times Q over N square root, if you notice the similarities right here. And why is it this way? Well, in chapter 13, part 1, we start with the truth, and then we use the truth to figure out something about the sample. In part 2, we start with a sample. It's going to block if I do that. We start with a sample, and then the sample tells us something about the truth. So if you notice right here, we're using the sample right here to make an interval for the true proportion. And up here, we're using the truth to tell us what we might see in a sample. So the questions differ a little bit. In chapter 13, part 1, you're saying something like, here we'll do a chapter 13, part 1 problem. It would say UT knows that 70% of students are in-state students. They take a sample of 200 students. How many? Random sample. Random sample of 200 students. How many would they, or what percent? Start here. What percent would they expect to be in state? So this is kind of the same thing we're doing right here, where we have the mean for the distribution of the sample proportion is equal to P. This is the same thing we wrote just a moment ago when we put this right here. That is the mean for the distribution. And so the mean for the distribution of the sample proportion is equal to P. The standard deviation for the distribution of the sample proportion, which is another question we could ask, which is just written that way. That's just read the standard deviation for the distribution of the sample proportion. That's standard deviation for the distribution of the sample proportion is equal to P. And so that's where we do the equation. Oh my gosh. I need coffee. I don't want coffee. I need coffee. Over N square root. That's where the standard deviation is. And just look at the spot it's in. That when you see this, the standard deviation is right here. So that's when we're drawing this out and we're saying it'll be normally distributed with a mean of p and a standard deviation of p times q over n square root. If you're here watching, feel free to say, hey, I'm going to double check. Oh, no. Oh, it is going. Good. I think everything's going. We have 2 people watching. Good. And this should be a public stream. Oh, we are on maybe a 6-second delay. Maybe it's going well. Awesome. Well, good. So we have the percent we would expect. And just think about this. If 70% of students are in state, then we'd expect 70% of students. That's what we expect. So this right here is P. So that's what we would expect. We would expect 70% of students in our sample to be in state. Right here is N, which is the sample size. And then we can also get Q. So Q is going to equal to 0.30, which is just the complement of P. So we've already figured out N, we figured out P, we figured out Q. So we're really good in this regard. We can erase this because that's just the same notation up top. And then we can draw the sampling distribution. So the sampling distribution is going to be normally distributed with a mean of 0.70. There's the mean. And then the standard deviation is going to be P times Q over N square root. Let's just write that up real quick. 0.7 times 0.3 over 200 square root. P times Q over N square root. So P times Q over N square root. There we go, 0.032. And this is the standard deviation, 0.032. 0.032. 0.032. My periods get lost sometimes there. So that is the standard deviation. And then we might ask, is something odd? Would it be odd to see 80% of students being from in-state? And I picked 80% for a reason when I saw the standard deviation. So we could ask, is 80% odd? If we saw that in this sample, would that be odd? And the answer is going to be yes. If you look at where 80% is, I'm going to round, 0.032. We can go right here, and we can go up and down. And what you do is you'd put 0.70 here, and then you'd go up 1 standard deviation each time. So it goes to 0.796. If you notice, this is right below 80%. So 80% is basically 3 z-scores. Could you go over how to identify the different types of samples when you have? Yeah, let's do that next right here. So we're finishing. Good to see you here, Zach. You got it. So if you look, this is about where 80% would be at. 0.80 is right here. You could also give a z-score to this. We can find the z-score for any p hat by doing p hat minus p over p times q over n square root, which is the standard deviation. And so all I'm going to do is plug in the numbers right here of 80%, which is my sample, what I saw in a sample, like a hypothetical sample, the mean right here, and then the standard deviation right here. And what you should get is you should get something just a little bit more than 3. So you kind of know you've done it correctly. If you say in a hypothetical sample, what's the probability of 80%? Well, 80% is 10% more. We divide and we get something just a little bit more than 3, which is where I was going with this. If you notice, this is just barely more than 3 standard deviations. When you put your z-scores below here, you see it's just barely more than 3 standard deviations. So that's what we got going on there. Let's hop back to that previous sheet, and we're going to do some sample survey definitions. Great question right there, Zach. Thank you for swinging by. Let's go here and start with convenience sample. Convenience sample data. I never spelled it right. I don't know how to spell. Convenience. There we go. It's such a weird word. So convenience sample, not random. When you select the first or closest things near you. So this is not a random sample right here. Do not think that convenience sampling is a good thing. It's not random. It's when you select the first or closest closest things near you. So this is not random, convenience bias, convenience sampling. And then we also have voluntary samples. This is also voluntary bias, not random. When people volunteer to be in your sample. This is just voluntary sampling. It's not good. I mean, sometimes you have to do it. You have to get volunteers, like say, hey, who wants to take a survey? Then there might be bias, especially if they know what it's about. These are not random types of surveys, and a lot of times we might just call this convenience bias or voluntary bias because you did a voluntary survey or you did a survey in a very convenient way. But the main ones people are usually wondering about are things like simple random sample. Now, this is random by nature. So let's go here and put random sampling methods. Random sampling methods. These are random sampling methods now. And these are the not randoms. So we'll just leave that in there. We'll put a really big, scary red right there, not random. We don't want people using these. These are not good sampling methods. So the simple random sample is going to be taken the following way. We're first going to give everything in the population a number. And then we are going to randomly select these numbers. Randomly select these numbers. So if you think about it, everything has an equal and likely chance of being taken right here, because we are going to give everything a number, and you're basically going to put it in a hat and randomly draw out these numbers. It's kind of like if I go over here to R and I say something like, okay, I'm going to give away a prize. Everyone gets a number 1 through 100. So let's go ahead and we're going to give the prize to number 19, number 19. So everyone got a number 1 through 100, and then I randomly picked a number 1 through 100. And so this right here is just taking a simple random sample. I could take more observations. I could say, let's talk to 20 people in the class. Okay, person 61, 19, 93, 39. These are the people who I'm randomly sampling right here with simple random sample. Or I could use my whole class. I think I have 340 students. So I'm gonna talk to 20 random students. So here's the 20 random students who I'll send an email to, and I'll follow up with them. So that way there's no non-response bias where they don't respond. And I'll follow up and I'll ask them a question, or it'll be like a longer survey. I'll say, you've been selected to take a longer survey, and I'll send it to these randomly selected students. And you notice they were all given numbers in the population. Every student gets a number, and then you randomly select. That's simple random sample. Next, we have a systematic sample. A systematic sample right here is pick a random starting point. Random starting point is picked, and then sample every kth. Oh, it didn't do it. Observation. So pick a random starting point, and then sample every kth observation. How would we do this? Well, let's draw it out, and then let's code it, because coding's fun. Everyone's like, no. So we have right here, we would have a number line going something like 1 through 100. So with this number line going 1 through 100, I'm just going to pick a random starting point on it. My random starting point is going to be this, 11, and I'm going to pick every fifth number after 11. So fifth is just arbitrary. Sometimes you try to space it out so it's kind of like spaced throughout the population. You want to pick something smaller than larger than 2, smaller than 100. I guess it depends. If you're doing cars and you're doing crash tests, you might crash test every 100th car. So you think if you go to Nissan, they're going to say, okay, every 100th car off the line, we're going to crash test. We're going to run it into a wall because that's our crash test. And we're going to see how it does this. So maybe every 100th car gets this crash test and every 200th car gets this crash test. And then we have some sort of, way we kind of cycle through the different crash tests. And so maybe it's every 500th car gets the front on hat crash tests, and hey, what's up, Ryan? Hey, what's up, Dan? Good to see you both here. Wow, both at the same time. So are you both the same person? And so we're talking here about a systematic sample. I chose a random starting point. I'm going to start at 11, and I'm going to sample every fifth. So I'm going to go to 16, sample it, go to 21, sample it. And you notice what we're doing is we're going to start at a random starting point, pick a random starting point. So you just pick a random starting point, and then you sample every kth observation. So you just go every fifth observation, every 10th. This can just be any number you want. Kth is just a placeholder, and you generally pick something that kind of works for spreading it out across your population. You kind of make this sample plan and say, okay, we're sampling UT students, so we're going to talk to every 10th student who walks out of the library. Or we're going to talk to every 6th student who walks out the library. It's a little bit arbitrary, but the better you make your sample plan, the better it works, and the better results you get. Like the more accurate, the more what am I looking for? I'm looking for the R word. I'm looking for, what is it? It should look representative. That's what I'm looking for. Representative. I could see it. It was like a big word in my head, and I couldn't think of it. So the next one we have is where people start to get really confused on these. Are there going to be a lot more multiple choice? There's a lot of multiple choice. There's a lot of true false. There's numeric entry, especially for things like this right here. This is multiple choice heaven right here. This is all the multiple choice. And this is where people get really confused on cluster sampling. Yeah, great questions right there. Good to see you here, Nikki, too. Everyone's here. Yay! So one things are put randomly into groups. So this is kind of a before thing. You don't really do this. So you don't really do this yourself. You don't put things randomly into groups. But then randomly select n of these groups. Now, I bring this up. I put randomly select n of these groups because I like your Kahoot. Yeah, I think the Kahoot's a big help. And definitely the better you do on the Kahoot, the more prepared you are, I think. Don't worry if you fail the Kahoot. It's all right. It's all right. Only one person got 100, and people will get hundreds on the test. You got to memorize? Yes. And so this is a thing that came up last night is a person said take one bag of M&Ms, but the M&Ms are randomly put into groups, which are the bags. Like you don't put all the bad M&Ms in one bag. You don't say, okay, here's all the crushed M&Ms. We're going to put all the crushed M&Ms in one bag. Or maybe they do that. They don't do that. And so now you're going to take a bunch of these groups, and that's the clusters. You randomly take the clusters, and then people forget the last part here is perform a census on the clusters. I like doing this in class because when I give someone the bag, I say, how many of these M&Ms are you going to eat? And they look at me quizzically, and they're like, all of them? And I'm like, yes, you're going to perform a census. So a census is when you take data on everything in that cluster. A census in a population would be everything in a population, but the census on the cluster is when you take data on everything in the cluster. So this sounds really complicated, but just think about it in terms of M&Ms. M&Ms are randomly put into bags. When you go to a factory, they're not going to put the bad M&Ms or the misshapen M&Ms or the M&Ms that are, broken into certain bags. The M&Ms are pretty much randomly put into bags. So the bags are the clusters. So this is cluster creation. And then you're going to take maybe 20 bags of M&Ms to see the quality of the M&Ms. So when you take the 20 bags of M&Ms, this is the selecting clusters. And then right here, data on clusters. This is where you take your data on clusters. So you don't really create the clusters yourself. They're kind of, randomly put by the population. If you had to guess, are there more questions? I think there's going to be fewer where you have to do math. If you think where you're going to do math, let me look. We got the cheat sheet here. There's some math in this, some math, some theory, more math than theory. Like I would say these are all estimates. I would say this is 75% math, 25% theory. Randomness is more like 75%. Oh yeah, that's correct. It's still this. And then now we get into the reverse split. This is like, I would say 90% theory. Or let's do it the same way we're doing it. I don't even want to make math questions with this. So here's my projections for it. And then we'll copy this down so that way we can use it. Probability, that's a reverse. And there's theory you can do, but that's a reverse of it. And this kind of holds, then it's maybe 75-25 for the remainder. I'd say 75-25 for the remainder. So you can see the more heavy, so 75-25 for that, and then 75-25 for this also. So if you put them under a black light, they're because I was planning on going off Canvas content. Yeah, Canvas content quizzes are a great way. I keep telling people the Canvas content quizzes are a really good way to see where you're at. If you can do the Canvas content quizzes, you're probably on track. If you can't do them at all, make sure to practice your Canvas content quizzes. Stratified sample. This is where acknowledge, a difference in the population. Sample the population according to that difference. Randomly. So randomly sample. Randomly sample according to that difference. So I think a lot of times people get confused on cluster and stratified because you're taking groups. And so this is where a lot of the confusion arises. They're like, wait, you're talking about a group, you're talking about a cluster. So if we do, let's say, freshman, sophomore, junior, seniors, are those clusters or strata? Would freshmen, sophomore, juniors, seniors be clusters or strata? I think we're on a pretty quick delay today, so hopefully someone answers. So would freshmen, sophomore, junior, seniors be clusters or strata? And look at the key ways that we start with these, and what would you do? Like step one should kind of make clear. Freshman, sophomore, junior, senior would definitely be this. Don't worry, a lot of people get this wrong. You got a 50-50 shot. Freshman, sophomore, junior, senior would definitely be this sort of sampling strategy. To say, let's look at the freshmen, sophomore, junior, seniors and use that in our sampling strategy. Oh no, don't worry. It would be strata. It's gonna be strata because we're gonna acknowledge a difference. So freshmen, sophomore, junior, seniors are different like class levels. And then we're gonna say, okay, we need this many freshmen, we need this many sophomores, we need this many juniors, we need this many seniors. Because if they're clusters, because I realize that it's like a group, it's like a bunch. Every time someone hears like, okay, a bunch of freshmen, it's like, okay, that's a cluster. But they need to be randomly put into these groups. And then what would you be doing if you treated them as clusters? You'd choose, like the freshman and sophomore clusters for UT students and sample all freshmen and all sophomores. And that wouldn't be representative of UT students to select 2 out of the 4 clusters and then to sample all those students. Does that make sense? Like you're looking to get a representative sample. So acknowledging the differences between freshmen, sophomore, juniors, and seniors, you would then, maybe you're asking, how has the coursework been this semester on a rating scale of 1 to 10, but 1 being very easy, 10 being impossible. And you'd want to, you wouldn't want to just talk to freshmen. You'd also want to talk to seniors and juniors and sophomores and, people from all different class levels to get a representative view of what people think about this semester. So you're acknowledging the differences in how different class levels might view it. You're not going to get all freshmen, all sophomores, all juniors, or all seniors. You're not going to treat it as a cluster. If we go to Domino's Pizza and we order, we want to see if they claim, Domino's Pizza claims that every slice of pepperoni pizza has at least 2 slices of pepperoni on it. So every slice of pepperoni pizza has at least 2 slices of pepperoni on it. So we go to Domino's Pizza and order 8 pepperoni pizzas. The pepperoni pizzas are all what? So we go to Domino's Pizza and we order 8 pepperoni pizzas and look at each slice on the pizzas. So we're going to try to look at the claim. They say they have a new commercial like each slice has at least 2 slices of pepperoni on it. And so we're like, oh, let's go check out this claim. They're like, Domino's Pizza's making sure pepperoni lovers really love their pizza with 2 slices of pepperoni on each pizza slice. So it's a pretty easy task to do. Just 2. That's all they need. We're seeing if this claim is true. So we're going to order 8 pizzas. And the 8 pepperoni pizzas we order, each pepperoni pizza would definitely be a what? Each pepperoni pizza would definitely be this is a reverse example now. Each pepperoni pizza would be a cluster because we're getting a cluster of slices. So we're ordering, if you think about a pizza has, 8 slices on it. So yeah, exactly. Is it a cluster or a strata? Because each pepperoni pizza is a cluster of slices. Does that make sense? Like we're getting a whole bunch of slices at once by ordering a pepperoni pizza because we're sampling all the slices. And then in this instance, we're sampling, here I'll say we're ordering 20 pizzas because there's 8 slices in a pizza. I don't want to confuse the terminology here. We're going to order 20 pizzas, and the 20 pizzas each have 8 slices. So how many samples are we getting by ordering 20 pizzas? Since there's 20 pizzas with 8 slices, we're actually doing 160 samples because each pizza has 8 slices, and then we have 20 pizzas. We're getting 160 samples by doing a cluster sample strategy. But what if they say our pizza top, every slice of pizza always has a topping on it. So now they're making this claim for different types of pizzas. So maybe we order 20 pepperoni pizzas, 10 onion pizzas. Got to get some onion pizza. I miss onion pizza. So I miss all pizza. And we get 10 pepper pizzas and 5 mushroom pizzas. Mushrooms are great still. I don't know what happened when I started liking mushrooms. That was the weirdest change in my life. I hated mushrooms growing up. Maybe I just had good mushrooms when I got older. But we ordered different types of pizza. So what are we doing now? If we order different types of pizzas to check the claims, the pizzas are still the clusters, which have a whole bunch of slices, but the different types of pizzas are going to be, can you write what you think would be the hardest question on the exam? Yeah, I'll do it here. I'll do it next year. Who does Zach? You were wondering about the different sampling strategies. Is this making sense right here, Zach? And then I'll do what I think would be one of the hardest questions. It's a good question, Nikki. That's a good question. It is so cold. I have my Deadpool blanket. Let's see some Deadpool. We'll get some copyright right here. It is so cold out. Here's Deadpool. Ah! There's Deadpool. What? I don't even know what he's saying. Or watch out. There's Deadpool right there. Woohoo! It is just cold today. Whew. Cold out. Just not using heat. Oh, you think it awesome Deadpool. So check out Deadpool movie if you're old enough. So Deadpool, great movie. Deadpool 2 was all right. Sorry, Ryan Reynolds. It was good. It was good. It was just wasn't Deadpool 1. I mean, that's what happens with sequels. Unless it's Dark Knight. If it's Dark Knight, then it's awesome. I had a choice between Deadpool and Attack on Titan. I was like, I'm going Deadpool. So here's one of the hardest problems on the test, or like a version of one that could be the hardest. Let's say you studied really hard for this test. Turns out that you have a probability of getting any question right. And turns out the probability is just, yeah, Mikhail, feel free to ask any questions. Turns out the probability you get a question right is this. There are 5 questions remaining on the test. What is the probability you get one or more wrong? Okay. So you studied really hard for this test. So now it's like, why is it not like adjectives? I don't know. It wants to delete those all the time. The world is removing adjectives. Really super hard. Guess what? You get another adjective. Yeah, of course you're gonna do that. Yeah, do you know the answer to this one? If you know how to do this one, it's not that bad. Yeah, if you can solve it real quick, you got it. So either you get them all right, or you get at least one wrong. Okay, I think I got the answer. I'm gonna do the answer off screen. That's not the answer, obviously. I'm gonna do the answer off screen, and then I'll show how to do it. 2, 3, 4, 5. I got it. I have the answer. Who else has the answer? Because let's think about this theoretically. I've got the answer off screen right here. But when you take this test, you'll either get 0 wrong, 1 wrong, 2 wrong, 3 wrong, 4 wrong, or 5 wrong. So this is how many questions you could get wrong. Oh, no, don't worry. I've got the answer off screen. Don't worry. Keep working it. I'm just making sure we don't have dead air. We don't have silence. So you'll either get 0 wrong, 1 wrong, 2 wrong, 3 wrong, 4 wrong, or 5 wrong. So what we're interested in right now is you get 1 or more wrong. We're interested in this. We are not interested in this. We're not interested in you getting 0 wrong. How can we describe someone gets 0 wrong? The way to describe somebody getting 0 wrong, nice job, you're totally right. Great job, Nikki, excellent work. That is totally the answer. Yep. So describing getting 0 wrong right here would be getting every question correct, which means you get the first correct, second correct, third correct, and fourth correct. And you see I'm saying and right here because you're multiplying all of these together. Great job. Yeah, I'm proud of you. This is, once you know how to do these, they're not that bad. It's people are like, I can't do this question. I'm like, you just got to practice it. You got to know how to do it. You just have to be able to describe it because this is getting everything correct right here. I don't want to look like we're dividing. This is the probability of getting everything correct. So the probability of getting everything correct is 0.9 to the 5th power. And either, because we can say right here, one of two things will happen. Either you will get all correct, I'll write all C, all correct, or at least one wrong, which is 1 or more wrong. So either you'll get them all correct, or at least 1 wrong. And you see, we just did it mathematically. You're either going to get them all correct or at least 1 wrong, which this is the when we say the probability of the sample space is equal to 1. So this is saying one of these things must occur. You're either going to get all the questions correct on the test for the last 5, or you're going to get one wrong. What about one right? That is complicated. I can show you that one. That won't be on the test. Getting exactly one correct is a little more complicated. Don't worry, that's not on the test because it requires permutations. I can show you that really quick. I'll show that next. And so now what we're going to do is we're just going to take this equation right here. I'm highlighting in green. We're going to take this equation right here, and we could do one wrong also. And we're just going to rewrite it. We're going to write it as 1 minus all correct equals at least one wrong. At least one W. So I'm sorry. So we can rewrite that mathematical equation and solve it for at least one wrong. And then all we have to do is solve for what's the probability of all correct. And all correct is this. We showed that earlier. That's the probability of all correct. So here's the probability of at least one wrong. It's 1 minus, and I've got it right here. I've solved out the equation. There's the answer. It's 0.4095. So yeah. And so yeah, we won't do it. We won't do one wrong. So here's the tough part for at least one wrong, or exactly one wrong. If you want to do exactly one wrong, then you have to look at it this way. When you take the test, here's what could happen. You could get a wrong, right. Let's do check marks. Those are easy. So X, check, 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 X, check, 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 X, check, check. Does this make sense, Nikki? What I'm drawing right here is, if you're saying if you get one question wrong right here, when you get one question wrong, it could be the first question, the second, the third, the fourth, the fifth. Like you could get this or this or this or this. These could be the patterns. Like if you say I got one question wrong, it could have been the second one you got wrong. I got one question wrong. Well, it could have been the fourth, or it could have been the fifth. And do you hear the or word I'm using right here? Because you can't get the second question wrong if you get only one question wrong, and also only get the fifth question wrong. So all of these are what to each other. Every single one of these are what events to each other. So every single one of these are what events to each other. So every single one of these, since I'm adding them. So if we say somebody took a test and they got one question wrong, all of these possibilities for what they could get wrong, and the equations are on the exam. Yep. Not the 1 minus. Well, the 1 minus for the complement is, but not the like advanced stuff we're doing right here. So since I'm adding these, this is key right here. This knowledge we should have like that. Since I'm adding these, I've identified that every single one of these is what of each other. And Mikhail, if you're still here, feel free to ask questions. Since I'm adding these are definitely what of each other, which is a condition for addition rule. Since I'm adding these, all of these things must be what of each other. They must all be disjoint. Since I'm adding them, they must be disjoint. If I'm multiplying, they need to be independent. So make sure you remember the disjoint for addition, right? You're just absorbing. That's awesome. I love it. So when we add things together, they need to be disjoint. Nice job, Zach, right there. We might be on a long delay today. We might be on the long delay. Trying to fix that. And so if you look right here, this right here is 0.1 from the previous problem. 0.9, 0.9, 0.9, 0.9. So these are the associated probabilities, but these all right here, every one of these would have the same. The math is just kind of mixed up. So in truth, what we have right here is we have 0.9 to the fourth power times 0.1. And then we just multiply this by 5 because that's really just adding it. And that is the answer to what's the probability you get exactly one wrong, which we won't do that. Don't do this. Let me put here, not on test. This part of it's not on the test right here. That's not on the test. The idea of disjoint, the idea of independent is on the test, and this used disjoint and independent. This is kind of the next step if we were to go further. And then the formula sheet. You can use the formula sheet. That's what you need to. Let's go grab the formula sheet. I am live streaming. 11 people, if you have a question, feel free to ask. If you're wondering about anything, any topic, let us know. It is your review right now. I love when we have at least a handful of people watching. It's really good. And I'm like, yes. So make sure to grab your formula sheet right here. And here's the official formula sheet. And we do see the rules right here that if two things are added together, they are disjoint or mutually exclusive. Those are the same words right there. I lost somebody as I was like, oh, we got 11 people watching this. One's like, I'm done. So they are disjoint or mutually exclusive. And then we see here two things being independent is when we can multiply them together. So you do have the rules. And then you have the complement rule right here, kind of in two separate ways. And you have the set of all probabilities is equal to 1 because it's everything that can occur. And then you have here the empty set, which we haven't talked about much. It's not going to be on the test. It's just saying the possibility of things that can't occur is 0. So things that don't occur, don't occur. Guess it's an important rule for probability. And so let's see here. What other big questions are there? What have we not covered that I wrote down today? We did decision trees last time. We could do a randomness one. I love randomness questions. So we could do a simulation one right here. Let's say, let's do this. Let's simulate some data. So we're going to do a simulation right here. And let's say we're going to simulate, let's simulate rock, paper, scissors. Your friend always throws unknown to, well, if you always know they throw rock, you can always beat them. So we could say, if you always threw rock but only played one game, what percent of the time would you win? And in truth, you would win, you should only win 1/3 of the time because rock beats scissors, breaks scissors. And then rock and rock tie, and then paper beats rock. Man, everyone knows rock, paper, scissors. That's such an old game. So we go here to sample. I wonder who made rock, paper, scissors. Like the first person was like, I'm making this game called rock, paper, scissors. Okay. And then, so this is going to give us our data right here to do the simulation. So you're always going to play rock. Whenever someone says play rock, paper, scissors, you're just always going to play rock. This is assuming that what people play against you is random. Oh, I didn't concatenate the vector. This is assuming what people play against you is random. It's probably not. Probably people like playing rock. A second grader, yeah. And that second grader forgot to patent it. That second grader never patented it. And a lot of times, I feel like when we do simulations, we usually do it this way, though. Really smart second grader. So usually when we do simulations, we do it this way. And everyone knows it's rock, paper, scissors, so we can copy it this way. Okay. So here's our simulation problem. This sheet. No. There we go. Okay. So we're playing rock, paper, scissors. So what we need to do is we need to identify in this rock is equal to 1. Paper is equal to 2. Scissors is equal to 3. So we're actually looking for the 3s right here, and we start identifying, and we say, how often would we win? And we've just done it, I think. Made too easy of a simulation, but how often would you win if you play rock, paper, scissors, and you always play rock? Well, you'd beat scissors. So rock, paper, scissors, you beat scissors with rocks. That's how it works. And this is 7 out of 20 times, which is very close to what we would get. So in 7 out of 20, you know, I think here's what we could do. We can do a bigger one. And let me do this. Let's do this. How often do you win at least one game if you play 5 games against people and you always play rock? So we're making this more complicated right here, and I need to write real bit quick of code. I could write out the numbers myself. It's going to be more fun if we do this. Let's do this. Let's go to sample 5 right here. And then we're going to go to 4. And we'll go here. We'll go I. And we'll do 10 simulations. And we'll go to cat. And this should do what I want it to do. No, I got to go. I know we have to do cat paste. And yeah, this is cat paste, not paste cat. And then we need to go to right here. Okay, we need one more. And now we go here and do \n. Did I do it? Oh gosh. What have I done, everybody? What have I done? I need to stay inside the sample. So I go right here, right? Yeah, it's the cat. What? Wait. This will start a new line, right? Oh, that's outside the paste. I mean the cat. Can't be in the cat. No. 2 seconds. Am I doing the wrong? I'm doing the wrong backslash. There. Wow. What is it? Hey, Brian, could you go over a problem with decision tree? Yeah, let's do decision tree next. As I break this. It's doing a new line there. Can cat use that? Oh, no. That's a bummer. So close. So close. We can do some decision tree stuff here. Let's do decision trees. So 2 seconds. Class is not over yet. Just pulling up some data right here. I broke that example. I broke it. Broke the example. Here's decision trees. So we talked a little bit about simulations. You should definitely know increasing the number of simulations makes the simulation better, i.e. more trials. So if you do more trials, you get a more accurate simulation. Doesn't mean what the results will be, but you get a more accurate simulation. Let's predict what income level somebody's family comes from. So it's multiple level. Here, let's do this. Watch this. Political view. Let's go here to the variable. And let's go to column. Where's recode? Recode. How am I losing my mind? There we go. Recode. We're going to call this person conservative. This person's conservative. This person's liberal. This person's liberal. And I think, can we remove the moderate have no values now? Good. Well, I could have done it the other way. Let's recode. Oh, and then we put in place. Sure, let's delete for now. And I'll do it. So this is polyview. There we go. And then let's select within polyview. There's so many cool things you can do. Oh, does it not have that level anymore because I did that? Let's sort it. 2 seconds. I'll show you what we're doing right here. We're just gonna have liberal and conservative. So we're moving out all the middle ground people. We're gonna do. Hey, Brian, would you be able to go over some of the? Yeah, which one are you wondering about? Put it in the chat, and then we'll do that here next. You got it, Kiana. You got it. And so now we just have liberal and conservative. So now I've just eliminated down just because I want to do a simpler problem, so we can do some really good predictive analytics on this. Let's go here to polyview. We do not want to use the other political view to predict it because that would explain all the variation because I created it from it. So remove out these. Now, one thing you should know instantaneously about this is we should not use things that are identifiers or act like identifiers. The reason I'm not using these is because this is my y variable, and this right here was what I made my y variable from. So, of course, if someone's very conservative, that'll explain if they're conservative. Yeah, here, we'll help. You got it, Kiana. Good to see you here. Oh, let's color the points. What? What did I do? I broke it. I must have deleted the very liberals also. Or the liberals. So I'm just not go too quickly. Did I delete them off? Apparently I did. 2 seconds, everybody. Can't remove everybody. Well, darn. Go here. And we're moving out the conservatives. There we go. I mean the moderates. And delete rows. Okay, now we have it. Now we should just have the liberals. And if you see right here, liberals and conservatives. Cool. So let's go back to our predictive modeling. And let's take all the variables here. And there's all the variables. Let's remove those. Put this in the X. Put this back here. We're back to where we started. And here we are. Color the points. Good. And we have conservative. Everyone sees right there red and liberal blue. And let's split. The most important factor in deciding somebody's, and I think this was a different political view, because this was their view on economy. So people's economic views are oftentimes controlled by their social views. So different issues right there. And then the next most important issue is social issues again. And social issues. You know what I'm going to do? Since that's such a boring thing, it explains 45% of the variation. So obviously, if somebody is more conservative on one, they're more conservative on the other. And if someone's more liberal on one, they're more liberal on the other. But that's so boring. We could have guessed that. I'm going to go back here and remove that variable because it's so powerful in explaining. just because it's a little bit boring. So let's go back here and remake our tree and do better splits. Age of the Earth. And then we have George Zimmerman, political issue. And so I'm just to get it evenly split right here. We've got marijuana usage. So the most liberal people are going to be, and this is from data, it only explains 13%. It's not the strongest tree right here, but if you see liberal right here is blue, the most liberal people are going to be people who say the Earth is a couple billion years old, and they are in a service, music, business, or other, or not in a fraternity sorority. You can do categorical or quantitative. Decision trees can handle categorical or quantitative as the X's or the Y's. They do not use indicators or things that act like indicators. So you can use quantitative. So we could split on a quantitative. Like if we go here to, because, it's so small. Oh, it's perfect. That tree, wow. Split specific, you could split on height. And you see it splits on people's heights right there. So we can split on a quantitative, or we could predict a quantitative. So if you notice right here, 100% of the people in this group are conservative. So you have people who say the age of the Earth is a couple thousand years and use marijuana and no. And then if we go to the Leaf report on this, the Leaf report right here, let's go to Leaf report, shows that 57 out of the 57 people are conservative. I don't understand the bars with the splits. Like is the red part the split on the left? Oh, so no, so these bars right here, do you see this right here, how this is like 30%, 10%, 8%, and none? That's this right here. So those bars you see are these bars right here. It's the distribution of the Y variable, Michaela. Does that make sense? So when you're seeing the amount right here, let's prune this back up to the very top. I hate that it always does that when we do this. If we prune this all the way back up to the top, what you're seeing right now is basically this is inverted. So this is the amount of people out of the 442, and these dots are the individual's people. So when you see this amount of blue right here, it equates to that. Then when we go to split, if you notice right here, we'll try to get this on the screen at the same time. If you notice, really, there we go. That's where there it goes. So if you look at the splits now, you'll see there's only 1, 2, 3 dots. I see only 3 blue dots, and that's 3 out of 90. Hey, Sarah, good to see you here. So you see the 3 dots right here, 3 out of 90. There's the 90. And right up here is the distribution of it. And we zoom really big. You can see the 1, 2, 3 blue dots. And that's the 3 blue dots that are here. There's 3 blue dots inside of there. And that's the 3 blue dots that are here. So each one of these, this is the distribution of the Y within the leaf. This is the distribution of the Y within the leaf. And this is the distribution of the Y within this leaf right here. This is the first leaf. This is the second leaf. Does that make a lot more sense, Michaela, right there? Hopefully, is it starting to... Sometimes you have these epiphany moments after you see it a few times. You're like, I get how to do the decision tree. Like, I get it. I get what these leaves mean, that this is the Y variable. So what could be a potential question on this tree? Some of the hardest questions. So we've had a lot of what is the hardest question today. Let's ask this question right here. So how many people, tree just wants to not do its thing. How many people who believe the Earth, hold the belief the Earth is a Earth, like, oh my gosh, what is wrong with me today? How many people, can't zoom out even, there we go. How many people who believe the Earth is a couple billion years old, how many of them are liberal? How many people who believe the Earth is a couple of billion years old are liberal? How many people? It says we dropped a frame. No. Oh, that's 2 hours ago, an hour ago. Okay, good. We're good. How many people who believe the Earth is a couple of billion years old are liberal? Thoughts on that? So what leaves are we looking at? We're looking at leaf 1 and leaf 2. Because these are from this, like right here, we're asking about this leaf right here. These are people who believe the Earth is, I cannot speak today for the life of me, is a couple of billion years old. And so this is leaf 1 and leaf 2, which means this is leaf 1 and leaf 2. So if you notice these numbers right here, 78 and 15, represents 78 people right here. I wish it highlighted that when I did. I wish when I went over this 78, this is what highlighted. And this right here is 15 people because this is leaf 2. Leaf 1, leaf 2, leaf 3, leaf 4. Leaf 1, leaf 2, leaf 3, leaf 4. So this 78 and 15, if you add them together, you will get, let's prune this right here, prune below, you will get 93. Yep, and that's the answer. That one tricks a lot of people because it requires to understand where the numbers are coming from, and then you're looking at a group that splits into groups. So there's 352 people from people think yep, and that's 352 people, and there's 93 right here. And when I merge it back together, you can see it. So yep. And here's the thing, though. Once again, never assume anything about anyone because no matter what group you're in, people are most likely to be this. Like, it doesn't matter where you go with this tree, even though people are more likely to be liberal in this group, no matter what split you're in, everyone in this is more likely to be conservative. So even if you're like, aha, the people who think this, or aha, the people who think this, well, everyone in this is more likely to be conservative. So we could split here again. Now we get it. Well, George Zimmerman. So there's something pretty political. And you can see the splits on right here where people remember George Zimmerman, Trayvon Martin. So whether people agreed or strongly disagreed, liberal was more likely to strongly disagree or disagree. But there are conservatives who disagree too. And there's liberals who are neutral, agree, or strongly disagree. So it's pretty... Does the exam open? It opens at 6. It opens at 6. So the reason we know it's 93, to go back to that question right here, prune below, the reason we know it's 93 is this leaf right here is composed of leaf 1 and 2. This is leaf 1, this is leaf 2, and here's leaf 1 and leaf 2 right here. Leaf 1 and leaf 2 has 78 liberals right here and 15 liberals right here. So 78 plus 15 means that this is 93. Does that make sense, Gigi? That this is 78, this is 15, and that's 93 right there. Because this splits apart into those lower groups. When you see this, here, I'm going to fly up to it real quick. I'm going to go, whoo. So up here at the top, you see that this splits into these groups right here. Awesome, Gigi. Great work. Let's do a little, we're going to end class today with a little 320. So let me go grab the 320. I'm really excited. I know a bunch of people are going to do great on this test. I have a lot of confidence in what people have been doing and practicing. It really comes down to watching the class, though, because it's a lot to learn. Some people are like, I'm going to cram it all the day before. And it's like, no, you have to hear things 3 times. You have to go over something 3 or 4 times. And by the 3rd or 4th time, eventually it starts to make sense. You're like, I get it. I get it. It's just I had this epiphany moment. All of a sudden, it started to make sense. It's crazy to think that's how things work, but it really takes... I liken it to playing songs on a piano. No one sits down and is like, I'm going to learn Rondo alla Turca in an hour. No, you're not. You're going to learn Rondo alla Turca, great song, over a course of a couple of days. It takes time. It takes practice. It takes making mistakes. It takes, just reviewing. So it takes a while to get this material down. You can't learn material just in a single night unless it's memorizing definitions, which some of this test can be. I think it was Kiana asked, so for 1B and 1D, part 5. 1B and 1D. Okay, let's find here. 1B. Wait, where's 1B at? Wait. If you're still here, Kiana. 1D. Here we go. Is this right here? Which model are we making? Oh, wait, is good. Oh, the scatterplot matrix? I think, are we making the scatterplot matrix? We definitely can do that. So the scatterplot matrix is going to be the pairs function. This is at the start of the multiple regression part 2 notes. And so, yep, scatterplot matrix, let's do it. So with this scatterplot matrix, and we're doing the effective average temp, which data set is this? It probably says EX4 bike, there we go. I knew it has effective average temp in it. So this is going to be the pairs. And we want to predict demand. And we're going to use all the variables. And data equals this. Now we have to load the data set first. Very important right here. Oh, I'll show you a quick trick right here. Oh, and then there we go. I didn't have reg class. What? Oh, because I didn't. Oh my gosh. Oh my gosh. I need coffee. I don't want coffee. I need coffee. You follow the same format as mingling. Yeah, basically. Yep, that's it. Y tilde x comma data equals, and we get it right here. So this is the format, and I'll show you something really cool, Kiana. Let me find this again. I always forget. Advanced. Maybe, is this it? I think I found it. I think I found it. Yes, yes, yes. Oh, these look way better. Here it is. Is it Psych? Do I have that library? Spell Psych. Okay. I must have updated my R. So I'm loading up a library right now. And then the function is pairs panels. What? Oh, do you have to do method? Really? What's it not like? Cycles built, error in argument length 0. Oh, do you just take the data frame? Oh, I think I know what it wants. It wants just the data frame. There we go. Cool. I like this better. That's pretty nice right there. And did they update it? What's this function? Oh yeah, they're doing it themselves. And then they do this. So this is just a quicker way to make it. Yeah, so I like this a lot right here, Kiana, because this might give some insight. We still have demand in the top right here. And one thing that might be confusing about this is here's all the relationships to demand to all the other variables. And do you notice any of them that appear to not be so linear? Like, which one of these maybe has some non-linearity to it? Demand with which other variables? Because I think this might clue in. Do you see how this is demand with average temp? Demand with effective average temp? Do you see how these are like paired up right here? Demand with average humidity, and then here's the correlation for all these. So we can actually look at the correlation for all of them, and then we can look at, we're mainly just focusing in on this and on this right here. Also demand looks to be, yep. So this might make a little bit more sense than looking at this, which is basically the same thing, but we at least get the linear plot through here and all this. So it's kind of neat. This is the pairs panel through the psych. If you saw the code I ran, let me put it all right here. You need to install packages. Do the install packages down below. But this, so do install packages. Really? Installed up packages and do psych down here. That way, don't put it in your document because that won't knit. So if you install this, how can you tell linearity? Good question. So that's why I like this plot right here because it makes it pretty easy to see. Where do you see an issue of linearity? And I really like they're putting a dot at the center of this. And then what do you notice about this? Or maybe they're trying to look for the nonlinearity. This is probably the most linear, even though it's not that strong. And look at this one especially. Now we're only focusing on these, but you see how they're putting a line through the data, and do you see sort of some bends through the demand and average temp? So that's where we see a little bit of nonlinearity here, a little more nonlinearity here. Not so bad of nonlinearity. It's kind of weak though. If you go to that, that's very weak negative. So there's a weak negative relationship. It's a lot weaker correlation. And then here you see also another weak negative, but mostly linear. So the stronger ones, which are demand, average temp, demand, effective average temp, have the larger portion of nonlinearity. And it's probably this outlier down here, which is pulling the line downward more. You can see this outlier pulling the line a little bit more down towards it. Does that make more sense, Kiana, to talk about where you see evidence of nonlinearity, if any exists, between demand and other temperatures? Because I really like this plot right here. I've used this plot before. It's just not base R. It's just a random package someone created. So, and you can download it too if you're watching this office hours, and it makes a really nice plot. So just make sure you install the psych library, and that just gives you additional functions. And then you can just make this plot like that. Someone created this, and we can use it. So these wouldn't be... I would say they're linear enough. I'd put that in quotes. Everyone's going to put in quotes on their assignment now. I'd say they're linear enough. This one's super linear, but has an outlier, but that's an XX relationship. But overall, there's some linearity here, which maybe we could use for linear regression. They're linear enough. There does seem to be problems where we see some sort of bends through the model for demand and average temp and demand and effective average temp. So I do have cause for concerns that, you know, we should look at some checks for the normality at the end of this to see if we have issues with normality of residuals or linearity of residuals. So that is important right here to see if it is linear. We can probably go ahead Probably. I'll show you a quick trick right here for, did you make all the individual models right here? So when we make individual models, here's a really cool trick. A really cool trick is going to be the following. Let's make our first model right here. This took me semesters to learn. I was like, wait a minute. It's not that bad. Okay, so demand, and we could just do this. We could, yeah, that's probably just as quick if you copy paste all of them. So we're going to do a demand data equals and ex4 bike. So here's our first model. And let's append this on. Here's our first model, and there's the coefficient. So the coefficient, do you see how this right here is the coefficient we have right here? Here's the p-value of basically 0. This, for all intents and purposes, is 0. And is it significant? It definitely is significant. But if we change this, demand is the first variable in the model. So let's go here and take, this is a little confusing, so let's take only rows 1 and 2, or columns 1 and 2, rows, columns, good. And let's run it again. And now look what we have. Now, and this might be confusing, don't do this if you don't want, but if you take a look at the model, let me zoom out one. Do you see how with this code, I'm taking the first and the second column of the data? The first column of this data is going to be demand. The second column is average temp. So next, I'll take the first and third, then I'll take the first and fourth, then the first and the fifth. And we can just copy this code right here and change it. Just change this. And now we've done it. So by using the positions in the columns, I'm able to easily change what variables I'm using. Oh yeah, I know, right? These are the things we should try to think of when we're doing code, because there's tons of ways to do this, but now I've just changed it so it just takes the variables I want, because this is just going to only use those variables. If you look, the only variables it's going to take, let's clear the output and then run it again. The only variables it's going to take are going to be demand and effective average temp. Then if we run this one right here, the only variables it takes to make the models, because it's using all of them, are going to be demand and average humidity. So if you run this, you can get the demand average humidity model, and there it is. There's the average humidity. So it's a much faster way to do it. Just confirm your numbers. If you're getting these numbers, you should be accurate. I won't show all the models, but yeah, and then you can copy paste the variables. And there's a ton of ways to do it, but I like this right here, because if you can copy paste code, it's like copy paste, copy paste, copy paste. But was there another one you were wondering about, Kiana? What else can I help out with? Oh, we got 45 minutes. I need coffee. When I can start drinking coffee again, it's going to be an amazing day. Probably about 2-3 weeks out from drinking coffee. What does D5 say? Where is it? What does it ask? I always hate when we put book questions on here. I mean, I'm responsible for this. So. Tell me a little bit what D5 is. Oh, is it right here? Wait, why am I not finding D5? Wait, where's it at? D5? Put a little bit of what is it D? In your opinion, is this a useful model for predicting demand? Oh, is it the full model? When we look at useful, just depends on which model we're talking about right here. Oh, is it right here? So I believe at this point you might be using the full model. And the full model, if you are using the full model, you're just going to be using this right here. That should be the full model. Good. So here's the full model, I believe. I called it M3. Don't call it M3 because we already used that. It's just easy to change it. So why not? Someone's going to call it M3. Let's call it MAll. Mall. It's called Mall. Or, okay, I'll be good with my file, my naming. Called m.all. There we go. It's the full model, yes. So great job, Kiana, right there. Excellent work, starting on this ahead. Excellent job. That's why I'm like happy to stay and help, because starting ahead is awesome. What do you notice right here that would be useful in this model? Like, what do you think is good? Like, what sounds like something that would be, and I think you might know the answer. What sounds like something that might be useful in helping us understand demand? If you're like, this might be a reason that it would help us understand demand. Like, what would be practically significant about this model? And I think you'll get it. Because when you see practical significance, you should go to a few things for regression. You should be like, oh, we should definitely talk about this. Like one of the main things. there's probably two numbers you should talk about. One of them would be this. The model typically misses the demand that we have for the model typically misses the demand for daily bikes by about 1,365. It typically misses the demand for daily bikes by about that much amount. But what's the other thing that maybe sounds a little bit better? R squared, exactly. And the interpretation of R squared would say 40.06% of the variation in daily bike demand would be explained by these variables in the model or the model itself. And that sounds pretty practically significant, that knowing these variables gets us about 40.06% of the way to understanding the demand for bikes. So I'd say, yeah, I'd say it's pretty practically significant because it definitely brings us a lot closer to understanding the amount of bikes we will need out for people to use. And there's a lot of relationships here we could exploit in a good way to, talk about how average humidity and average wind speed impact. But then you can go crazy. Don't do this. Don't do this. This is like the next assignment. What's that got? 50%? Yeah, and the R squared just got a little bit hurt. So now 50% of the variation. Look, only one p-value is really significant. This one is significant, but only one is super significant. We got a big interaction right there between those two variables, the average temperature and the effective average temperature. But I think that's got it. Was there another one you're wondering about? Feel free to ask. Was there any other? I'm gonna try to figure out all this Streamlabs stuff. I might have to do some late night test streams and do just random streams to the YouTubes. I think that's got it. Great job, Kiana. Great job, 201. Don't do the full interaction model. So if the code for the full interaction model is this right here. But don't do the full interaction model. We're not doing the full interaction model. So don't do the full interaction model. Because then we'll be talking about interactions next class. Today, for some reason, morning class, we didn't get through that much material. So don't worry, today's a lighter class, but definitely attend. I haven't looked at the other questions yet. So for now, great job, Kiana. You got this. So I'll let everyone go. I'll be online soon again, teaching 320. See you soon. Great job, Kiana. Keep up the good work. Bye, everybody. Bye.